history about our own universe. Something that was kind of discussed a few months ago and something that we've known about for just over a few years now, but something that still doesn't have a good explanation and seems to be even more mysterious than a few years ago. We're talking about what's known as the Hubble tension. So here's how this is right now. When it comes to trying to explain the universe, there are obviously a lot of different ideas and a lot of different theories out there. But when it comes to astrophysics and when it comes to astronomy, it's the direct observations that matter. When the scientists see something, and also when they detect something that can either explain new phenomena or can potentially confirm previous phenomena, that's really when it gets exciting. Which is actually pretty much exactly what just happened now with the recent study that you can find in the description below. So let's actually kind of talk about this. And let's start with a bit of a history. So back in 1915, Albert Einstein published his famous general theory of relativity, which within only a few years becomes a fundamental theory potentially explaining the universe around us. After about 2 years, he adds a constant to this.
Yo, Journalist, what's up?
A constant that we refer
How you doing?
to as the Einstein
Welcome,
constant.
welcome.
And
Happy
whole purpose
life,
of this
yo,
was to basically
exactly.
ensure that the universe was
Workout,
static. It
speed
wasn't
run,
moving anywhere, it wasn't
chat with
expanding, it
Journalist.
wasn't shrinking.
Happy
But
life.
later on, Einstein realized that this
Thanks
was
for being
the
here.
stupidest mistake of his life.
How are
At
you?
least that's what he called it. Because by 1931, he finally accepted the idea that it was an expanding universe after all, like suggested by some of the other scientists, including Hubble, the French Georges Lemaitre, and the Russian Alexander Friedman. And so by 1931, the formula was reworked to have a kind of a constant expansion value, suggesting that the universe was expanding constantly throughout the entire time and space. And this pretty much kind of stayed like that for a very, very long time. But then in 1998, which was
I'm great. Not gonna lie, how are you? I'm great. I'm great too. Thank you.
Three astrophysicists, Sol Perlmutter, Brian Schmidt, and Adam Rees, identified
It's nice and
something
sunny today
really
too.
unusual
I'm
by
gonna
looking
go out
around
after
the
work.
universe
I'm on my lunch
and
break.
looking
I'm
at
using my
various supernovae
lunch
out
break
there.
and the 2
They
breaks to
realized
stream
that
this.
the universe isn't just expanding, it's also accelerating its expansion. It's moving faster and faster and faster. And eventually they won the Nobel Prize for this. And so once again, it was really the observations of these unusual events that sort of allowed us to understand something else about the universe that we didn't know before. Now today, the explanation for this is the mysterious dark energy, which by itself does not really have a very good explanation, mostly because the theory and the actual observations don't really match at all. But
Wow.
over the past few years, as the scientists started to analyze the
It's been a few
expansion of
days
the
since I
universe
lifted,
the
and it's
acceleration of
pretty
the expansion,
sunny for you.
we're essentially
Nice.
trying to identify what's known as
These
the
weights are
Hubble
feeling
constant.
really heavy.
We started to see new patterns emerge,
It's been a long
patterns that
time.
didn't really make sense. So some of the initial studies established the Hubble constant at approximately 73 kilometers per second per megaparsec. This basically means that for every 1 million parsec, or for every 3.26 million light years that we travel, the universe accelerates its expansion by about 73 kilometers per second. So that was fine and all, but then some of the other observations, using some of the other
Too
methods,
sunny.
for
What?
example, using some of the nearby stars,
Sun is
known
amazing. I
as
love the sun.
Cepheid variables, which normally blink or change their brightness quite specifically. So they actually allow scientists to establish very precise distances to various locations in the galaxy. And also by using various types of type 1a supernova, which normally explode with a very specific brightness, once again allowing the scientists to establish distances, the values started to change a little bit. At first it was 68 kilometers per second, and then with pretty much every single observation, the values changed once again, with some of the more recent observations visible right here in this picture. And what's interesting is that some of these observations were extremely accurate. They had an extremely low error. Obviously comparing this to some of the observations from X-ray observatories or from Hubble telescope. But if you were to sort of draw a line through this, you would not be able to capture all of these observations.
I already don't like
In other
warmth,
words,
and
it
now
was
this.
as if the
What?
values
I
for
love the
Hubble
warmth.
constant
I love
were
it.
different
This is my
depending on
this is
what
my
location we're
beach
looking
there.
at, or what time period we're looking at. With
Not
some
my
of the
beach,
new
but you know what I
values
mean.
that you can see right here in this table. And so something was definitely not adding up.
Oh.
Moreover, depending on the technique used, the values always congregated around the same number. So for example, all of these red observations you see, these were done using extremely old cosmic microwave background, and so they essentially showed us the universe long time ago. Whereas a lot of these observations in black, these were from some of the more recent events or from some of the closer regions, such as for example from nearby galaxies, from our own galaxy or from the galaxies not too far away. And so the values seem to sort of correlate with the distance away from planet Earth. And so just to see what's happening here and possibly discover some other unusual patterns, the scientists whose paper you can find in the description decided to analyze around 1,000 different supernovae from various regions in the universe, obviously created in various times around the universe, and decided to see if they could maybe connect this to some kind of a other element or some kind of a other constant. Or actually, more specifically, they wanted to see if this could be explained if the constant was not constant at all, if it was actually a dynamic value. And so by combining all of these different observations from different previous studies, and by also mixing and matching various results, making sure that there's no biases and no potential errors, they came to a somewhat not surprising conclusion that everything seems to fit perfectly if the Hubble constant changes with time or if a kind of a time element is added into it. Or by turning the Hubble constant into a Hubble variable that varies with time, a lot of their calculations seem to
I'm a
match
winter
actual
kid. Oh, that's okay.
observations.
That's cool.
But this is just a preliminary
Oh,
first
I'm
study.
definitely a
The
summer
scientists in the
person.
study do
I
mention
love the
that
sun
a
so
lot more
much.
supernovae are needed to make sure that, first of all, there is no bias in, for example, observation. For all we know, maybe a lot of these supernovae were just kind of in the right location at the right time. Maybe if we were to turn around and look at some of the other objects, thousands of other supernovae in some other galaxies, maybe this particular result would actually disappear. And so that's kind of what the next step is going to be. These scientists will be trying to find more supernovae to study and try to see what's going on with those as well. But I guess the more exciting part is, of course, if they're correct. If the Hubble constant is not actually constant and if it has changed over time from about 68 kilometers per second per megaparsec to about 73, well, in that case, well, first of all, this does actually create a bit of a problem for many different formula, for many different estimates, and even for the age of the universe as we know it. It means that a lot of things will have to be recalculated. At the same time, this also implies that, well, there are obviously a lot more things going on here. It's either completely new physics, something entirely different nobody understands just yet, or possibly something to do with gravity that we just don't understand. One of the potential explanations here are essentially a group of ideas or theories referred to as the modified gravity theories. And here there are actually quite a lot of different explanations and quite a lot of different ideas that generally try to explain the universe without the use of things like dark matter, dark energy, and so on, and instead modify formula from Einstein and from Newton, making everything fit slightly differently. But that's of course just an assumption for now, just a preliminary explanation. Chances are that maybe in about 10 years from now, just like it happened back in 1998 when the scientists originally discovered that the universe was accelerating, now someone else might end up winning a Nobel Prize for trying to figure out what's happening here as well. Nobody really knows what it is. Obviously no one has any good explanation, even though there are quite a lot of explanations, but there's definitely no one explanation that seems to explain everything we're seeing. There's always something that doesn't make sense, which of course is actually really exciting because the less we know and the less we understand, the more likely we're going to be exploring and learning and possibly discovering new things for many years to come. Because, you know, if you actually discover everything about the universe, well, everything sort of becomes really boring. And so I'm actually super excited to keep learning about this, to keep
All day
trying to
too?
understand what's going on, and then really all
That's
this
great.
to you as well through these videos. Anyway, once we discover more, I'll make sure to follow this up with another video.
So basically he's saying that the
Check out
expansion of the
paper and all
universe
the relevant
might
links in the description
be
below.
faster
Subscribe
than
to this channel, share
previously
this with someone
thought.
who loves learning about space and sciences,
That's the
and maybe connect
TLDR
to
of
learn
this.
something else. Maybe support
He
this
says,
channel
what
Patreon
if
by joining
the
channel
Hubble
membership
constant
or
isn't
by
actually
buying the
constant,
person t-shirt. You can
saying
find
that
in
the speed of the
description.
expansion of the
Anyway,
universe might actually be
anyways,
accelerating from 69 whatever to 73 whatever. Which is super interesting. Because I mean it's like still expanding and even increasing in speed and expansion. It's really interesting stuff.
wonderful person, this is Anton, and today we're going to be talking about some of the new discoveries coming from the Voyager 1 probe that's essentially the farthest object humanity has ever built, somewhere out there in the interstellar space. But today I wanted to discuss the mission as well, and also just talk about what the scientists found, what it means to our understanding of the galaxy and the universe, and more importantly, remind you of some of the coolest achievements of this mission. Now, as you probably already know, Voyager mission is basically two different probes, Voyager 1 and Voyager 2, with both probes taking a slightly different approach or slightly different path out of the solar system. Voyager 1 took this path, flying by Jupiter and Saturn, whereas Voyager 2 also got to visit Uranus and Neptune, with both probes obviously being exactly the same as well. But the mission itself would not be possible without these wonderful people from JPL, who essentially proposed this and further pushed for this mission to be developed in the early 70s. But originally there was actually only one person that sort of made all of this story.
Outlast.
It was this wonderful person, Gary Flandro.
What's
And
Outlast? I don't know what Outlast. Tell me about it.
Completely by accident realized that in the late 70s, all four planets, Jupiter, Saturn, Neptune, and Uranus, are going to align with one another in such a way that you could actually send a spacecraft visiting all four planets using previous planet to provide what's known as the slingshot maneuver. So here, Jupiter, Saturn, Uranus, and Neptune align in just a perfect way to create an opportunity for what's known as the Grand Tour, visiting all planets, or in this case 4 major planets, with a single mission. And that's basically how the Voyager mission was born. One of the most ambitious, if not the most ambitious, NASA missions ever. Something that cost them close to about $1 billion. And this is actually something that happens once every 175 years. So the next time this is going to be possible, I don't think most of us are going to be around anymore. But the thing is, the original mission design was really only set up to have these probes function for 5 years. From 1977 to roughly around 1982. At least the Voyager 1 probe. Voyager 2, because it also got to visit Neptune, was supposed to function until 1989. And so nobody could predict or expect the probes to function for so long. They've been actually communicating with planet Earth for the past 43 years, as of today, as of 2021. And moreover, they're still actually doing a pretty good job at also sending us a lot of data. NASA created this website specifically for the Voyager missions, allowing us to see the mission status and also showing us some of the parameters that they also get to detect here from planet Earth. It also shows you which instruments are still functioning and which ones have been disabled because there's just not enough power. And more importantly, it also allows you to see exactly where the probes are located in comparison to everything else in the solar system. Earth, by the way, is somewhere right there, very, very close to the center of the solar system. But until 2012, pretty much all of the observations we've been making with all of the other probes as well,
I'm not a big
what's known as the Helios.
I'm not a big horror game fan.
Really,
I liked
really
Half-Life.
Plasma bubble that's formed by our sun as it starts emitting various solar winds and a lot of different particles.
That's cool, Journey. Are you thinking of playing it? Streaming it?
Particles. But in 2012, Voyager 1 probe left this particular region and entered the actual interstellar space. These scientists got to detect the Helios sheath here, and there was quite a lot of exciting reports about this back then as well, and now it's traveling in between stars, it's traveling in the interstellar space. And a few years ago, when Voyager 2 also reached this particular location, we also got to understand that this whole Helios sheath is almost like a plasma wall. It's basically a relatively thick region that both probes had to pass through. But what's really cool about both of the probes is that they've been continuously sending all of the data back to scientists, allowing them to study specific electron densities or plasma densities of various regions in the interstellar space, allowing the scientists to start mapping what happens in between stars as well. And there have already been a few pretty interesting discoveries. One of the most recent and most unusual discoveries is in regards to what NASA referred to as the plasma hum. Essentially almost like a humming noise of the background plasma that seems to be present across the interstellar space. And very recently, the NASA scientists were able to convert all of these observations into the actual sounds we can hear as well. Now you're going to hear them in a few seconds, but essentially this is what we're looking at. Now this is from between 2012 and now, and notice how there are at least 2 different spots here that represent some sort of a really, really major plasma wave. But let's just actually hear this first.
That's
And so
crazy.
these seem to represent some sort of interstellar plasma waves of what seems to be really large chunks of plasma, or basically gas that's ionized. And according to the scientists, similar observations have been done pretty much every single year. So there are these really large chunks of gas that seem to be spread out across really large, vast distances of space in between stars. Now, right now we believe that there are possibly three ways that these can be generated. The smallest
Oh,
of these
last two
objects
started living
most
them.
likely
Nice. That's
just come
cool.
from the interactions or from the effects from our sun. And so in this case, various solar eruptions and various shock waves produced by the sun very likely just disturbed the heliosphere and expanded just a little bit, producing these tiny chunks of gas. Now this one here is a little bit exaggerated, but this is just to give you a visual perspective. And so the smallest ones that were detected so far were very likely just produced by the sun and various eruptions. And even though I'm saying small, in terms of the actual size, these would be anywhere from a few million to possibly a few billion kilometers or miles in size. A lot of bigger ones that have not been observed yet would also be produced by various ancient supernovae. Now we've seen these with various telescopes, we just haven't seen these with the Voyager craft yet. And all of them you can explore on this map that's available in the description below, with the nearest one, the one we're flying through right now, known as the local interstellar cloud. You can sort of learn more about the ideas behind this and what possibly created this in one of the videos somewhere right there. But some of the biggest of these unusual gas clouds and these plasma clouds in the interstellar space are probably created by the galaxy itself. With some of these gas clouds visible as these darker patches all over the galaxy. This is formed by the motion of the galaxy as it rotates, and as various masses interact here, they essentially create various gas-like formations inside galaxies all over the place. But once again, this is not something that the Voyager probe just saw. It only saw the ones from the sun. And in case you were wondering how it's able to do all of this after 43 years, well, the answer to this is, first of all, is this, the reactor, the RPG that's using nuclear energy to generate electricity, still has approximately 75% of material able to produce energy and provide enough wattage for at least 3 more years, possibly even
Nice.
4 years. But the actual detection is done with these two long antennae you see sticking out on both sides. These are plasma wave antennae, and they both are able to detect the minute vibrations of electrons near the spacecraft. And by detecting those vibrations,
I had
it
two
can
because
then
my friends
proceed
played
the
too.
intel and transmit all the data back to Earth. This is known as the Voyager's plasma wave system.
That's
And
cool.
what's really unusual
No
is
worries.
that
You don't have to do
after the
anything that
Voyager
your
left
friends
the
do.
solar system, the actual density of electrons
If you don't
increased by
want to.
about 40 times.
I mean, if you
And
want
so
to, that's
it
cool.
reached the current levels back in 2015. Which sort of
That's
implies
funny.
that the plasma levels outside of the solar system are slightly higher than just inside of it on the outskirts. But this is of course something that NASA is hoping to learn with some of the new missions, including the currently planned mission that's going to be specifically for the interstellar space. If it ever occurs, it's going to go into the outskirts of the solar system much faster than any craft before, and it's going to reach the same regions of space in only a few years. But right now this is still being planned, and it's not even certain if it's ever going to happen. But if this mission does happen, it's going to be a really exciting mission to follow, because it's going to help us explore the interstellar space and answer a lot of the questions about the universe, the galaxy where we live, and of course our own existence as well. For now though, we still have approximately 3 to maybe 4 years before Voyager probes officially shut down and officially sort of become retired, but until then the scientists are going to try to get as much data from these probes as possible. In 2025 we're going to come back and talk about this once again. Until then, thank you for watching, subscribe if you still haven't, share this with someone who loves to learn about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.
Oh man.
Hello wonderful person, this is Anton, and today we're going to be talking about some unusual and unexpected discoveries in regards to neutron stars and more specifically pulsars. Discoveries that imply that these objects are way more extreme and way more unpredictable than we originally thought. But also discoveries that help us understand the universe in general. Because obviously when it comes to studying the universe and trying to understand how the universe formed, how the universe is structured, or what's going to happen to the universe in billions of years from now, we really need to study some of the most extreme objects in the universe. This is how we can kind of find some of these answers. And the most extreme objects just happen to be, and there's actually one right here in the middle of this nebula. These objects are neutron stars. The objects that represent the most extreme types of matter possible in the universe. The matter that becomes so extremely dense and so extremely pressurized that it's literally on the verge of collapsing into a black hole. But since it's not a black hole yet, it really shows us the physical limits of the universe. And generally these objects have always been super interesting for most of the scientists. First of all, originally when the scientists discovered them, they actually thought that maybe this was aliens talking to us, because of the pulsations and the radio emissions. Some of the first pulsars were referred to as little green men, LGM for short. But with time and with theories, the scientists realized that this is basically the matter right before it collapses into a black hole. And within only a few decades, the scientists started to make some really extremely accurate observations and of course analysis of these very beautiful and very mysterious objects. As a matter of fact, one of the best observatories of pulsars or neutron stars is actually in space. It's this beautiful telescope known as NASA's Neutron Star Interior Composition Explorer, also known as NICER, that, as you can probably see from this video, attached to the International Space Station. And this observatory is so accurate that it can even allow the scientists to try to determine the size of these objects. And remember, we're talking about objects that are thousands and thousands of light years away from us, and their size in general is really only about maybe 20 to 30 kilometers, approximately 15 to 20 miles in size, while also allowing us to study some of the other properties as well. But even after a few decades, we still seem to find some discoveries that kind of surprise us. And specifically by studying this pulsar right here, and another one I'm going to discuss in a few minutes, the scientists were able to discover something that made them scratch their heads and realize that we still don't really understand these objects very well. And so the first pulsar that the scientists analyzed is known as J0030. It's around 1100 light years away from us, it's approximately 1.4 masses of the Sun, and it spins approximately 205 times every second. Now this pulsar is so powerful and the magnetic field here is so strong that it literally ends up stripping some of the material from the surface and then redepositing it on the other side or somewhere else on the surface of the pulsar. And because of this, there are certain regions of the pulsar that become extremely hot and produce a lot of X-ray radiation. These are known as the X-ray hotspots, and you can kind of see the simulation of these X-ray hotspots right here. Now what's interesting about pulsars and neutron stars in general is that because they basically bend the light around them, and specifically right near the surface of a typical neutron star, because of this you can actually see some of the regions that you would not be able to see otherwise. In other words, some of the light from the back of the neutron star is bent and is emitted toward us. And so it sort of looks like this. And because of this, not only can you see the back of the neutron star and thus be able to see these hotspots even if they technically face the other side, at the same time, because the light from here is also bent and sent toward us, overall the neutron star, if you were to look at it, would actually look larger than it technically is. And so even though we have the sphere that's about this size, what your eyes are going to see are going to be a sphere that's around this big. And back then the scientists were able to determine that its total size is approximately 25 kilometers or almost 16 miles in size. But obviously it would seem much bigger because of these light banding effects. And so interestingly, these hotspots technically don't actually ever disappear. They're always visible even if the neutron star spins around and turns its back to us. The light banding effects kind of make us see it from every side. Nevertheless, some of the new observations suggested that despite of that, these unusual formations tend to sort of concentrate in the southern hemisphere of this pulsar, and there seem to be maybe 3 of them. So it might actually resemble something like this, or more specifically maybe even something like this. But I guess one explanation here is that, well, the magnetic lines generally don't really necessarily have to be symmetrical, so maybe these unusual spots just follow the magnetic lines. But that's just one of the discoveries. The other more major discovery is from another pulsar that the scientists also analyzed. The pulsar known as G0740. This one is about 3 times as far away at a distance of nearly 4,600 light years away from us, and this one is known to be one of the most massive neutron stars ever discovered. It's almost at the limit of being a neutron star, roughly around 2.1 masses of the Sun. Today, the scientists believe that anything above that and the neutron star collapses into a black hole. So these particular neutron stars are extremely interesting, mostly because the scientists want to figure out what exactly happens to matter itself in these extreme conditions. There are generally two propositions here. One proposition suggests that the neutron star becomes extremely squishy, and maybe the matter on the inside starts to collapse into something a little bit more exotic, and the neutron star eventually starts to shrink in size. In other words, the more massive the neutron star, the smaller in size it would get. So that's of course one proposition. The other proposition is that, well, it maybe still maintains its shape and size because something else entirely happens on the inside, but the exotic materials might not necessarily appear, and the neutron stars might still have a lot of neutrons on the inside, thus the name, and also a lot of quarks that tend to interact and tend to stay strong and maintain the shape. And so trying to figure out which of these predictions is more correct is basically what the scientists were trying to do here. And they did this once again by trying to measure the size of these neutron stars. But obviously, because these objects are really small and also extremely far away, we can't just measure the size by looking at them directly. The scientists here use a clever technique that tries to measure the differences between arrival of different X-rays that tend to be affected by the gravity coming from the pulsar itself. And so by measuring these really minute differences of like nanoseconds, the scientists can then work out the gravitational potential of a typical pulsar, thus determining its mass. And if you love math, the math is all here, you can check it out in the link in the description. And once they know the gravitational potential, they can usually work out the size of the pulsar afterwards. And in this case, for this second pulsar that is way more massive, almost double the mass, the size turned out to be really similar, about 25 to maybe 27 kilometers, which of course implies only one thing, that the neutron stars do not seem to be squishy. They don't seem to have this exotic matter on the inside that reduces its size. They do seem to contain a lot of neutrons and a lot of really strong, really stable quarks, which to some extent is a little bit surprising. It's surprising that the neutron stars do not actually get smaller in size as you squeeze them and as you create more gravity. White dwarfs, for example, do this as well. They do actually decrease in size as they acquire mass. So do brown dwarfs. But it seems that the neutron stars are an exception, and because of this, scientists will probably be studying this for many years to come, trying to figure out what happens inside these very extreme objects. But then there was also another unusual discovery coming from this paper, something that tells us that this image right here of a pulsar is not entirely correct. Turns out that even though for the most part we normally see pulsars as this, basically you have a beacon with two different lights in opposite directions, the observation from both of these pulsars I've discussed presented an entirely different image, an image that you see on the right side. The pulsars do not seem to have these symmetric magnetic fields and do not seem to produce symmetric astrophysical jets. The jets can point in pretty much any direction because they follow the magnetic lines inside the pulsars. In other words, this is incorrect. This, however, is a much more likely scenario. And so all of these simulations that we have where the pulsars have these beautiful symmetric jets, they're all technically extremely simple and very likely do not represent the reality. The reality seems to be that there could be two jets pointing in one direction, there could be even three jets, and possibly even more depending on what's happening with the magnetic field in that particular pulsar. And since we've discovered around 2,000 neutron stars so far, it kind of would be really interesting to find out if this applies to all of them, or if there are some other exceptions that we're not aware of right now. But most importantly, trying to study these objects and really understanding what happens inside of them can definitely help us answer a lot of fundamental questions about the universe and everything in it. For example, we know that neutron stars are responsible for producing a tremendous amount of various elements that we have on the planet that are only produced in, for example, neutron star collisions. And because there are so many different elements like gold and platinum that are produced in these particular events, and also because there seems to be so much gold everywhere, it does create a very interesting and very intriguing question of, well, first of all, how many neutron stars collided in the past? How many different neutron stars are out there in the galaxy? And also, what other roles do they play in the formation of various elements and various things in the universe? Maybe they're also responsible for some other mysteries we're currently not aware of. We already know that, for example, FRBs, fast radio bursts, are potentially created by a type of a neutron star known as a magnetar. But chances are we're going to discover a lot more mysteries and possibly even a lot more solutions of other mysteries by studying these unusual and these extremely mysterious objects. But anyway, for now that's all I wanted to mention in this video. Check out the relevant links in the description below, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Either way, stay wonderful, and as always, bye bye. Hello wonderful person, this is Anton, and today we're going to be talking about yet another unusual discovery that seems to present us with a solution to another interesting mystery. The mystery of this unusual astrophysical jet that seems to suddenly bend by about 90 degrees and going in a different direction for some unusual reasons. And this is in a galaxy or a galactic cluster known as a Bell 3376. And so today we're going to be talking about this paper right here that investigated this cluster, used a supercomputer to simulate some of the effects in this cluster, and pretty much found a really cool technique for discovering magnetic fields in galactic clusters. But first of all, magnetic fields. So today we know that pretty much most of the objects in the universe to some extent will have some sort of magnetic field around them. So for example, obviously our sun, with the magnetic lines creating a lot of different effects on the surface. Obviously our own planet has a magnetic field that's responsible for protecting the atmosphere and a lot of other things on the surface. But even as we move out of the solar system and start looking around, we start discovering certain effects of the magnetic field there as well. So one local example is the local cloud. It's this unusual formation that's a few light years across that's basically a gas cloud. But the Voyager probes discovered that it also seems to possess quite a strong magnetic field, which essentially holds this cloud together, and there are a lot of these clouds all over the galaxy. Now the magnetic field here is obviously not as strong as the planet Earth, but it is strong enough to more or less keep this cloud as a cloud for millions and millions of years. But then over the years, as the scientists use various types of polarized light telescopes to try to investigate Milky Way galaxy and some of the other galaxies, they came up with several techniques to see these beautiful magnetic fields in various galaxies near us, and of course in our own galaxy as well. So this one here is from Centaurus A, with the magnetic lines visible as these structures you see on the picture. And here's sort of what our own Milky Way looks like if you were to try to visualize the magnetic lines stretching across the entire galaxy. And so a lot of these magnetic fields do interact with gas in the galaxy and to some extent guide it and move it around the galaxy, in some cases even helping galaxies grow. But when it comes to some of the strongest and most powerful magnetic fields, there's really no comparison to what we can find in the middle of a typical galaxy. So these supermassive black holes in the middle, with their extremely large and very energetic accretion disks, can usually generate magnetic fields that are so powerful that they end up creating the jets that you see. And so today the explanation for these so-called astrophysical jets is basically ridiculously powerful magnetic lines that snap once in a while, producing these jets. And as you might know from some of the previous videos, the material in these jets can move to really close to the speed of light, with the most famous such jet being the one from the galaxy known as M87, the galaxy famous for that first picture of a black hole. This jet is about 5,000 light years in length, and it's also produced by these very powerful magnetic fields near the black hole. But some of these jets can be way longer and be produced by much stronger magnetic fields. And I've actually talked about some of them in some of the previous videos. But here we're really talking about magnetic fields in general. So it seems that everything in galaxies has magnetic fields. But what about outside of galaxies? What about the intergalactic space? So what about the space between galaxies, such as, for example, in large galactic clusters, where there might be a lot of gas and a lot of interaction as well? Would those regions also have magnetic fields? Well, until now, it was pretty much impossible to know. Obviously, there were speculations, but there were no observations. And without observations, it's just a hypothesis. But the scientists behind this study decided to investigate the famous cluster known as Bell 3376, located about 600 million light years away from us, That's particularly interesting because in the middle of this cluster, the most powerful and the brightest galaxy with the biggest black hole seems to have this strange astrophysical jet that suddenly turns 90 degrees and goes in a different direction, and also seems to do so on both sides. And that by itself is first of all a mystery, but also an opportunity to study possibly magnetic fields in these clusters. And that's the assumption that the scientists made here. They used the computer simulation to try to recreate some of the effects that a potential magnetic field in these clusters would produce. And by using a supercomputer known as Aterumi 2, which is the most powerful astronomical calculations supercomputer, they were able to create a model that more or less showed them what most likely happens in this jet and how this jet is very likely affected by the magnetic field between the galaxies. Realizing that what's happening here is most likely described in this picture. We have these two jets coming from the black hole, and then they actually collide with something invisible right here and create a kind of a backflow that then creates the mushroom-like formation we see here and here. But interestingly enough, afterwards, some of these particles end up being re-accelerated and moving in this direction, which is also visible here as well. And the most likely explanation here is literally some kind of a very powerful magnetic wall, or a wall-like formation with a lot of magnetic force that can literally stop an astrophysical jet, in some sense very similar to what you see here. A spray of water that gets bounced off by the asphalt or by the road itself, which of course means several things. First thing is that now we seem to have a technique to potentially observe and map all of these invisible magnetic fields by using nearby astrophysical jets and the interaction of particles coming from the jets and then somehow redirected by the fields, while at the same time developing a really interesting computer technique that can then recreate some of these effects and obviously allow the scientists to explain what sort of a field might be present in the region and what kind of interaction we can expect from some of the other nearby objects, or essentially allowing us to now see magnetic fields present outside of galaxies that most likely interact with galaxies in some way or another. Now obviously this here only shows us one of these magnetic layers, but the scientists in this paper speculate that there are probably several different magnetic layers present in between of these galaxies, and by using this technique we can probably start mapping everything, figuring out what sort of a magnetic field all of this forms. And so far the preliminary simulations indicate that the magnetic field is basically sort of C-shaped, like you see right here, with an unusual double formation that you can see forming here, that seems to extend all the way across for millions and millions of light years, sort of wrapping this whole galaxy around. And considering the jet here is several 100,000 light years long, this is a huge structure. You can basically fit several Milky Way galaxies in there, and it also seems to be a relatively strong structure. And so I guess the question is, what exactly formed it? And the explanation that the scientists provide so far is sort of related to the way that the galaxies interact with one another. As they move around and as they sort of pass through each other's regions, they usually leave behind a lot of different wakes, a lot of gas-like formations. You can kind of see some of them in this simulation from the Illustris project. And once these wakes start to form around these galaxies and around these clusters, which by the way also relates to this unusual Large Magellanic Wake that is created around our own galaxy, and that's also a video you can check out on the channel that should be popping up somewhere right there. What this suggests is that these gas formations and these wakes seem to be present in most clusters and very likely have these very powerful magnetic effects. Although this type of an effect is definitely rare, this is something that we haven't really seen very much, which does suggest that the magnetic field for this particular cluster seems to be extremely strong. And so this unusual comet-like structure that's several million light years across is most likely formed by some sort of a gas discontinuity right in this region that produces these magnetic fields as various types of plasma gas interact with one another. And since the jet particles seem to be re-accelerated in two directions right here, it only reinforces the idea that right in this region there is some major magnetic field interaction, very likely formed through some sort of a galactic interaction previously, where several galaxies might have collided and created some sort of a density discontinuity, or in simpler terms, a really large plasma cloud with a lot of charged particles. In some sense similar to the local cloud I mentioned previously, but with extremely powerful magnetic fields able to redirect an actual astrophysical jet. And so obviously by using a similar technique, the scientists can now start mapping the magnetic fields in other galactic clusters as well, and possibly even start mapping intergalactic space that up until now was more or less invisible to us. Which means that we can now start exploring the previously invisible areas between galaxies and discover what hides between them by studying the effects from these jets striking those regions and possibly being deflected by them. Now obviously this doesn't happen with all the jets, and a lot of the jets are just straight and end up producing something like this, but there are definitely a few galactic clusters, usually more massive and ones with a lot of interaction, where some of these jets do form unusual shapes, which means that it will definitely allow scientists to start mapping that space, allowing them to visualize what sort of hides between the galaxies in those regions. But I guess until we discover more, or until we find some other unusual jets out there, or solve another mystery, that's all I wanted to mention in this video. Pretty interesting study, really interesting analysis, and a pretty cool discovery. But for now, that's pretty much it. Thank you for watching, and subscribe if you haven't. Share this with someone who loves learning about space and sciences. Maybe come back tomorrow to learn something else. And maybe support this channel on Patreon by joining the channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Either way, stay wonderful. I'll see you tomorrow, and as always, bye-bye. Hello wonderful person, this is Anton, and right now we're flying through our own Milky Way galaxy. As you can kind of see from this simulation, there are a lot of stars out there. Billions and billions of them. The approximate estimates suggest that there could be up to about 400 billion stars in the Milky Way galaxy, but relatively speaking, they're all kind of far away from one another. And because of this, we never actually expect any of these stars to collide with one another. So these star collisions generally don't happen. But stars do come close to one another, and sometimes really close to one another to even disturb the star system and potentially even steal a planet or two. And today we know that in the past at least a few stars did actually come pretty close to our own solar system, with one such star I discussed in this older video that you can find somewhere right there at some point during this video. Now how this influenced the solar system we don't really know, but it most likely had some effect. And I also mentioned in that video that these approaches do happen relatively frequently. But what about the next approach, or the next star that's going to come close to the solar system? Close enough to potentially disturb some of the outer planets, or maybe cause some sort of a disturbance in the Oort cloud, and potentially even cause certain comets to come close to the inner solar system, maybe even leading to some sort of a major impact event on one of the planets. And there's at least one paper that came out recently, the paper that as always you can find in the description below, that used some of the recent and most up-to-date data from ESA's Gyges telescope, has been creating an extremely accurate map of all of the nearby stars that a lot of scientists have already used to learn quite a lot about our own galaxy and some of the nearby locations close to planet Earth. And interestingly enough, in this data they identify at least one star, a relatively unknown star, that's slowly inching toward the solar system, and that's going to pass by the solar system extremely close to us in approximately 1.3 million years from now. And considering that Oort cloud, as you see right here, starts at a distance of about 1.6 light years away from us, with the inner edge being roughly around 1000 astronomical units away from the Sun, it is a little bit unnerving to know that this particular star is most likely going to pass through the entire cloud itself, approaching us as close as 0.06 light years away, or roughly around 4000 astronomical units away from the Sun. Although more realistically though, these types of disturbances of the Oort cloud do happen pretty much all the time. Mostly because there are three several effects that always influence the location of these comets, and they do get disturbed by other things as well. So it's not just stars. As a matter of fact, a star passage would be extremely rare, so these comets do get disturbed by other events much more frequently. For example, in one of the previous videos, I mentioned the existence of this map right here that shows us all the nearby objects within about 30 light years away from us. And I've also mentioned in several videos that currently the solar system is flying through this region known as the local cloud, local interstellar cloud. but it's also flying next to another cloud known as the G cloud. And essentially by flying between these two very massive regions, there's quite a lot of disturbance happening right now, with one major disturbance that's going to happen in about 10,000 years when the sun is going to exit the local cloud and very likely stay in between clouds and then enter the next cloud, the G cloud, that's also going to disturb the comets once again. Now obviously what happens to those comets is another question, nobody really knows, it's extremely difficult to predict, but I guess the worst case scenario would be this. This doesn't happen very often though, and so a much more likely result is just a lot of comets coming within the inner solar system and creating a lot of light shows, but also creating a lot of interplanetary dust. But because normally it would take them about 1,000,000 years to get to the inner solar system after they get disturbed, we obviously still have a few thousand years, actually close to about 900,000 years, before we can actually even see any effects from the passage through this local interstellar cloud. But there's another effect that a lot of comets experience. It's the effects from the galaxy itself. It's what's known as the galactic tides. Now these tidal effects happen all the time as the solar system orbits around the center of the galaxy, and this is something that we also don't really know how to predict, but these galactic tides are very similar to the tides we experience on the planet from the sun itself. And so for example, even though the majority of the tides on the planet are from the moon, some of the tides on the planet are also from the sun itself. And similar to how the tides from the sun affect the water on Earth, the galactic tides tend to stretch and pull on the Oort cloud, eventually disturbing some of the comets and maybe even causing some of them to once again come closer to the inner solar system. But when a star goes through the Oort cloud and disturbs it, that's actually an extremely rare event. Although because of all of the data collected by Gaia telescope, that is one event that is now a lot easier to predict, simply because Gaia telescope created an extremely important and extremely detailed database of all of the nearby and even not so nearby objects in the galaxy. But when detecting a star that's possibly coming toward us, we obviously don't just have to know the distance to it, we also have to know the declination, the velocity, the ascension of the star. And by using all of these details that are provided by the Gaia telescope, it's possible to sort of calculate the trajectory and the potential intercept of a star with another star. And this is related to a branch of astronomy known as astrometry, measuring precise motions of objects in outer space, which is literally the main purpose for the Gaia Observatory. It provides all of the necessary data and all of the necessary properties for every object out there. Although the original mission was the Hipparcos mission, which was also by the European Space Agency, and this only lasted
I might
for
ride
about
the
4
bike and
years,
then
back in
I might be
1989
done
until
after that.
1993. And so by analyzing all of the stars
I'll
in
see
the
how I
database,
feel.
and also by estimating their trajectory going back and forward by about 5 million years, in this paper the scientists identified several interesting objects. Now their Gaia database name is basically sort of like this, but some of these stars obviously have different names already, with this star in particular being the one that seems to have the closest approach. And in this table here you can kind of see that the scientists used 3 different methods, including methods that took into account the motion of the stars around the galaxy, to try to find out which one would come the closest. And this one star, the one with the name right here, seems to be the candidate that's going to approach anywhere from about 0.02 parsec to about 0.051 parsec away from the sun. This is going to happen in about 1.3 million years. Now, as I mentioned previously, that's about 4,000 astronomical units away from the sun, which sort of puts it right here at the closest distance. So it's kind of going to go through most of the Oort cloud. But the thing is, we've already known about the star coming really close to the solar system from some of the other studies as well. The thing is, this particular analysis seems to be very accurate and does suggest that it's going to come even closer than we originally thought. And the star is Gliese 710. It's a slightly smaller and slightly less massive than our own Sun star. It's approximately 0.6 masses of the Sun, and it's about 63 light years away from us right now. Now, we haven't really found any planets around it, even though there are some in this simulation, but chances are we are going to be finding those planets as we keep looking at the star, because it is a typical object where we usually find planets. And also, being a K-type star, it's an extremely interesting object because normally these types of stars have a much longer lifespan compared to our Sun, and also have a tendency to have habitable zones with very stable conditions. So if humanity still exists in approximately 1.3 million years from now, and if we still haven't discovered how to travel across distances or how to visit other stars, we just have to wait long enough for this star to come close to us so we can actually try to get at least here. Basically interstellar travel by waiting. And that would make a pretty cool science fiction story as well, by the way. But in this table you can also find some other stars like this one right here and this one right here that are going to approach the solar system even sooner, but at a slightly farther away distance. And because in this study they also went back in time, they also discovered this star that we've already known about that did pass through the solar system around 3 million years ago. And because of this passage, some of the comets 1 million to 2 million years ago might have actually increased collision chances in the inner solar system. Now when it comes to these collision events, or at least the presence of comets in the inner solar system, as I mentioned, there's a delay of about 1 million years, and it only increases the chance of the presence of the comets in the inner solar system by just a little bit, with the total number being about 12 comets per year, meaning that the chance for a major collision is still extremely small. But the chance for something like this is slightly higher. And the big emphasis here on slightly, it doesn't increase the chance of comets by that much. Nevertheless, still a really cool discovery and a really cool analysis. And once we learn more about what actually happens to various star systems when these nearby passages happen, we might actually discover some other effects as well. For now, we're still kind of not sure what exactly happens to star systems when one of the stars passes through the Oort cloud of another. Because it most likely happens quite a lot throughout the lifetime of a typical star, we don't really expect this to be a very spectacular event. But the thing is, it's still really difficult to predict what's actually going to happen to planets or even comets when these star passages occur. So we don't really know if the star that probably has its own Oort cloud can maybe somehow share all of this material with the inner solar system as it comes close enough to the Sun. Maybe by sharing these materials, this is how some of the planets might get materials they would not get otherwise. But that's of course just a speculation, and there's really no way for us to prove any of this just yet. But I guess for now all we can do is just keep looking, keep analyzing, and keep trying to find out what happens to planets and stars when this does occur. For now though, well, that's all I wanted to mention. Check out the paper in the description below, all of the relevant links and data there as well, and subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something you might have not known. Also, maybe support this channel on Patreon by joining the channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Either way, stay wonderful, I'll see you tomorrow, and as always, bye bye. Hello wonderful person, this is Anton, and today I wanted to discuss this, in my opinion, absolutely extraordinary story of, I guess in some sense you would call it detective work. Or to be more exact, the flash of light back in 2018 that resulted in a meteorite that spread across a really large area over the past 2 years has been so thoroughly analyzed by a wonderful team from the SETI Institute that they were able to discover everything about the asteroid, even when it originally came from and when it was created. More specifically, they were literally able to trace back the time and identify that this piece of rock that you see in this picture was released through a collision with Vesta asteroid approximately 23 million years ago. And just the fact that they were able to do all of this simply based on a few pictures here and there is really mind-blowing. Honestly, this is something that would make Sherlock Holmes kind of jealous. But to help you understand how absolutely amazing this new paper is, which by the way as always you can find in the description below, let's start with baby steps. So a few decades ago, scientists tracking various asteroids made an assumption that one day we'll be able to track the path of every asteroid and we'll be able to predict where they're going to land, and thus obviously be able to prevent their collision with planet Earth. All of this is essentially part of the so-called planetary defense. But back then, it seemed like science fiction, although this recent paper makes it a little bit closer to reality. And although these types of tiny rocks don't really pose any threat to our planet, by being able to track these rocks and predicting their path, we're basically kind of learning to do this with other rocks as well, specifically the ones that would be potentially dangerous. So our story starts on June 2nd of 2018. The Mount Lemmon Observatory picked up an unusual rock on the way, potentially, to collide with planet Earth. But the rock was really tiny, and unfortunately a few hours later, the rock was lost. But also at the same time, several different reports from Botswana, a country in Africa, and nearby countries indicated that something definitely collided with the planet because there was a very large flash in the night skies. Something that's indicative of what's known as an air bolide. Now, these collisions obviously happen all the time, and there are a lot of reports from across the planet, but what's unusual about this report is that it was originally detected as still approaching planet Earth, and so this is technically one of the only detections of an asteroid before it collides with the planet. The only other detection being this one right here from 2008, known as 2000 TC3. And surprisingly, this was also from Africa, but from Northeast Africa. With the important part here being the ability to track these asteroids and to also further recover them for further analysis. And so some of the scientists from the SETI Institute jumped on the opportunity to maybe also find this particular meteorite as well. But they really took it to a completely new level. They wanted to find out everything about it, including potentially the origins. But how do you even find these rocks? It's literally like trying to find a tiny pebble in an ocean of really tiny pebbles. And so to try to figure out the trajectory and the potential collision site of this meteorite, the scientists decided to combine as much data of previous observations as possible. For example, they were able to find the observations from the University of Arizona that showed the approach of this asteroid prior to its collision. They also then worked out the angles from all of the pictures they received and were able to triangulate the approximate location where this asteroid landed. And by combining the observations with the trajectory calculations, they were able to work out the dispersal area for where they might find all of the fragments. Now, this by itself is already a tremendous achievement, just figuring out where this tiny rock probably landed on a relatively huge planet. And to make things a little bit more complicated, it turns out that the meteorite and all of the fragments landed pretty much in the middle of a national park known as Central Kalahari Game Reserve. You know, that place that has a lot of giraffes, elephants, and lions and leopards as well. And so because of this, when traveling to this location, the SETI scientists had to hire a lot of local help, a lot of guards basically. But within 5 days, along with the local guides and representatives from the Botswana Geoscience Institute, this person right here that you see in the picture, they were able to find their first fragment and then more fragments and eventually recovered all of these different pieces you see right here. So quite a lot of different fragments were recovered and they were pretty happy with their discovery. 23 different pieces, all of them suggesting that they all came from the same meteorite, similar in composition to what's usually referred to as HED meteorites. And HED in this case stands for Howardite, Eucrite, Diogenite meteorites. All of them believed to be coming from the asteroid known as Vesta, which is of course the second largest asteroid in the asteroid belt. And although normally most scientists would be more than happy with these discoveries and would probably call it a day, the SETI scientists from the study took it a step further. They decided to really find out everything. How long did it travel across space? What part of Vesta did it come from? Can they actually answer all of these questions? And surprisingly, the answer to all those questions was yes, they were able to determine pretty much everything. And that's where officially my mind was kind of blown. I really didn't expect someone to be able to answer all of this in such a brilliant way. So first of all, they decided to name this asteroid Motori Pun, which is apparently a name of a local watering hole where a lot of animals congregate and basically drink water, near which the asteroid was actually discovered. And because this asteroid is now sort of seen as a national treasure in Botswana, they decided to give it a Botswanan name. And the first step here was to use various observations of orbital parameters to establish if it could indeed come from Vesta. The orbital analysis did show that the origins seem to be from within the inner asteroid belt, pretty much exactly where Vesta is located. Quite a lot of various asteroids have already been discovered with relatively similar orbits also coming from this direction, and they all have been linked to Vesta as well. But the next question was, of course, well, how old was it? How long did it spend in the outer space? Now here the scientists use a technique that relies on a simple idea that when in outer space, the asteroid is going to be bombarded with various cosmic rays. This will actually change the surface of the asteroid, producing certain isotopes, and the longer it spends in outer space, the more of certain isotopes will be available. And these are generally called cosmogenic radioisotopes, and they've looked at quite a lot of various isotopes in this case. For example, chlorine, beryllium, aluminium, and the analysis here suggested that the meteorite was most likely about 23 million years old. which means that it was originally released from Vesta about 23 million years ago. Now, you might already know about the Dawn mission. This was the NASA mission that spanned quite a long time around Vesta and around Ceres. It studied them in a lot of detail, analyzing every single crater, studying every single part of the surface with a lot of detail. And all of the craters and all of the formations on Vesta are well known today, including some of the craters, such as, for example, Antonia crater, which has already been identified at approximately 22 million years old and as a potential source of many different meteorites coming to planet Earth. So basically about 22 million years ago, something collided with Vesta, releasing a lot of the meteorites into outer space. And a lot of these rocks, after orbiting the solar system for 22 million years, are slowly falling onto planet Earth. And so initially scientists thought that maybe this asteroid also came from Antonia crater as well. But turns out something wasn't adding up. Specifically, chemical composition was a little bit different. And in this particular case, some of the phosphates inside the Matoripan asteroid suggested that it was actually melted once again sometime around 19 million years ago. And this of course implied that another crater had to be identified. And it didn't really take them long to discover the potential origin of this asteroid, the crater known as Rubria. It sort of looks like this. It was created about 19 million years ago, still has signs of the collision when it actually happened, and seems to meet all of the criteria needed to explain the origin of this particular asteroid. And so basically by combining the chemical analysis with trajectory analysis, with a lot of analysis from other asteroids that came from Vesta, they were able to specifically identify the location where this tiny rock was created approximately 19 to maybe 22 million years ago. By the way, I'm saying maybe here because the true age of the collision is still not really clear. It could have happened within about 4 million years of that particular period. But just the fact that the scientists in this paper were able to pinpoint the pretty much exact location of where this came from is really, really mind-blowing. This is like detective work of a completely next level, literally extraterrestrial detective work. And so because of this, when I finished reading the study, I was really surprised. I was really shocked by how accurate and how specific everything was. Just the fact that they were able to discover 23 pieces after just seeing a report of a flash in Botswana, just the fact that they were able to track this all the way back in time to Vesta, and then even identify the location of where this asteroid came from, this is just way, way too cool. And if they could do this today, imagine what we'll be able to do in a decade from now. Being able to predict where things will collide or if they collide, and most importantly, being able to somehow protect our planet from potentially dangerous collisions, that's what it's all about. It's about protecting the species and the biosphere of our planet. Now remember reading the original proposition for planetary defense back in the early 90s, and one of the ideas there was essentially suggesting that had the dinosaurs basically had space program, they would have never gone extinct. And
Thank
so
you for
by
being
being
here.
able
Thank you,
to
Journey.
achieve
Thank
these
you,
tiny
whomever's
baby
here. You
steps
guys are the best.
and getting to the point where we can finally protect our planet
You
from
guys
these
and
really
gals are
dangerous
the best.
collisions,
Thank you.
that's really what it's all about. This is the most important part of these types of studies, and this is why it's important to continue this kind of work. But once we discover something else, or once the scientists achieve a new groundbreaking discovery, well, I will talk about that in some of the future videos. For now, that's pretty much it. Thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and check out the paper and relevant links in the description below. Maybe support this channel on Patreon, maybe support this channel by buying the Wonderful Person t-shirt, or by joining the channel membership, and either way, I'll see you tomorrow, stay wonderful, and as always, goodbye.
Wait, thank you so much for being here. Okay, I'm just gonna sign off. Thank you for being here. I appreciate it very much. Thank you.